Uh, Now we shall be looking at fatigue loading of helical compression springs. In quite a few applications, the springs will have to sustain millions of loading cycles, and we'll now be seeing as to how to estimate the factor of safety in such sort of situations. Now, there are a couple of works with regards to how to approach this problem. One of the works which is used quite extensively is that from Zimmerli from 1957. So, what has been observed in this particular work was for a wide range of spring materials and size and tensile strengths, the infinite life was actually achieved under similar set of min and max stresses. So springs are normally made under two sets of conditions, unpinned and pinned. I am not sure how many of you are aware of short pinning, but short pinning is a surface modification technique where very hard particles, typically either ceramic balls or hardened steel balls, are impinged at very high velocity against the object which you would like to surface harden, in this case springs. So if you do surface pinning, then in that case compressive residual stresses are achieved, and the range of stresses, the range of max shear stress and min shear stress for which infinite life is achieved is widened as compared to that for the unpinned springs. So this is one piece of information which is available, which is that the range of stresses over which infinite life is achieved is fixed irrespective of the material and the size that we are dealing with. Now, uh, okay, so using this information, thus for example, if you are dealing with an unpinned spring, let's say with ultimate shear strength of 1480 MPa, then using modified Goodman criteria, we have that okay, the mean shear stress divided by the ultimate shear stress plus the shear stress amplitude divided by the endurance strength in shear is equal to 1, and then using this you can get the endurance strength in shear to be 324 megapascals. Okay, so this is one uh, way to approach the problem. Another thing which has been observed, or another observation has been that if you are dealing with polished cylindrical specimen, then uh, within the irrespective of the mean stress that you are applying, the stress amplitude is at which failure is observed is essentially constant. This particular model is referred to as Sines failure criteria. Okay, and only thing is for this failure criteria to be applied, the maximum shear stress has to be less than the shear yield strength of the material. One point to be noted whenever we are using this Goodman criteria or any other fatigue failure models is that the ultimate strength in shear for materials is observed experimentally to be 67% of the ultimate tensile strength of the material. Please note that the relation between strength in shear and strength in tension is different, a little different from the relation between yield strength in shear and yield strength in tension. And that is because ultimate strength is related to failure of material, and it's also affected by pressure, unlike that of the yield stress, so initial yield stress. So anyhow, so when you are dealing with ultimate strength in shear, you please take it to be 67% of ultimate strength in tension. So the way we normally approach the problems is, in any problem the max and the min load which the spring is subjected to is given. Using that you get the mean force which the spring is subjected to, and as well as the amplitude of the force which the spring is subjected to. Then you use the relation between maximum shear stress and other relevant parameters in order to get the mean shear and the amplitude of the shear. So let's look at a problem in order to better understand how to approach problems for shear. So consider example 10-4. So what you are given over here is you are dealing with a helical compression spring with a wire diameter of 2.3 mm. Outer diameter is which is actually equal to the mean coil diameter plus the wire diameter is 14 mm. So based on this, you can estimate the mean coil diameter to be 11.7 mm. The spring index turns out to be 5.1. The free length is given as 98 mm and number of active coils is given as 21. So based on these two pieces of information, you can, and it's a squared end conditions, squared and ground end condition. So for this, you can estimate the total coils as equal to number of active coils plus 2, which is 23. The free length to be equals to pitch times the active coils plus 2d, and yeah, the the free length is this thing, and the solid length is equal to d times nt. Now the spring is unpinned, and the minimum and the maximum stress which the spring are subjected to is 25 newtons and 156 newtons. So the first objective over here is to estimate the safety factor against fatigue using a torsional failure criteria using the Zimmelai data. So for music wire in question, the ultimate tensile strength is 1959 MPa for 2.3 mm diameter wire. The ultimate strength in shear would be 67% of that, which comes out to be 13 MPa. From Gerber criteria, the endurance strength can then be estimated as 262.9 MPa. So remember that the stress amplitude is 241 MPa and the mean stress is 379 MPa. This would be fixed basically for whatever spring problems that you're going to solve. The stress amplitude and the mean stress at which infinite life is achieved is fixed. So based on this and a failure model, you can estimate the endurance strength of the material. Now in this problem, the min and the max load are given. Based on that, you can get the mean force to be 90.5 and the amplitude of force to be 65.5 newtons. Using the formulae relating the force and the shear stress, you can estimate the mean shear stress to be 285.3 MPa and the amplitude of the shear stress to be 206.5 MPa. Then as per the Gerber failure criteria, then we can get the safety factor in fatigue using this relation. You can estimate that to be 1.19. Now if you were to be using the Sines failure criteria, then in that particular case, NF is defined as the stress amplitude at which failure is observed divided by the shear stress amplitude in the application in question. So once again, from Zimmelai data, the stress amplitude is 241 MPa, and in this particular problem, the shear stress amplitude is 206.5 MPa. So based on this, you get a factor of safety of 1.17. The spring constant is obtained through this relation to be 8.4 newtons, and then based on this, the spring weight is estimated to be around 0.25 newtons, and the fundamental frequency can be estimated to be about 292 hertz. It's said that in this case the excitation frequency is 20 hertz, so the ratio of fundamental frequency of spring to excitation frequency is close to 15, so it's just all right. But well, you may change the spring design parameters so that this ratio further increases and at least lies somewhere in between 15 to 20. That's it.